Well, thank you very much, and good morning, everybody. My name is Florence Sanchez. I'm a professor at Vanderbilt University, and my presentation today is going to focus on the effect of Halloysite Nanoclay on the performance of 3D printed cement-based materials. And I would like first to acknowledge my co-authors, Dr. Michael Cosson, who did his PhD on that research topic, as well as Dr. Lisa Brown, our research engineer. So I'm going to change a little bit what we have been doing in 3D printing. What you talk about, I'm going to look at a different application that diverges from the large-scale on-site 3D printing, and that is more oriented toward precast fabrication of blocks and bricks and small elements. So much of what we have heard this morning about 3D printing has been on this, the application has been for large-scale element and structure, and the technology hold promise for improving the construction process by increasing the productivity, accelerating the construction speed, providing design flexibility as well as freedom, architectural freedom, and reducing waste. And all of this, and that's what we heard this morning, has been done through adaptation of traditional cement-based mixture. However, there is another application of 3D printing that is 3D printing can be used for designing and creating novel material. The small-scale 3D printing provide the ability to optimize the microstructure and implement hierarchy of structure and patterns by using infill patterns. And I think that's one of the advantages of 3D printing that we are not using enough in the field. Okay? So this is the what my group has been focusing on, looking at developing this 3D printed architectural concrete. And again, the application here that we see is for precast fabrication of bricks, blocks, and or small elements. So the 3D printer that we have been using is this, it's a gantry-style printer. We can print specimen on the centimeter scale with a relatively good accuracy. But something that I wanted to point out here is the size of the nozzle tip. Okay? Here we are looking at filaments that have a thickness than less than 2 millimeters. And this is it's an important factor because it's going to have some important characteristics or some important mechanism on some of the things that I'm going to be talking about today. Okay? So the advantage of small-scale 3D printing is that we can tailor both the geometry and the composition. And the goal is to be able to manipulate this, to manipulate the properties. So there's been some research on customization of the mechanical properties or control of crack propagation. And my group has been focusing more on developing this material for efficient thermal transfer and energy management. And we can see on the slide here, we have different architecture, and that provide different heat transfer inside of the material. So 3D printing on the small scale expand considerably the design space. Now we not only have to understand the link between the composition and the material property, but we also have to understand the link between the geometry of this internal architecture, the composition, and the material properties. One other aspect is that by printing and trying to control the material, we also need to have a better understanding of the filament formation and the properties. And so what I'm going to focus on today in this presentation is going to be talking about the filament formation and the property of the filament. So as we heard this morning, in order to be printable, the cement ink must meet certain requirements. We need to have extrudability, meaning that it needs to be sufficiently fluid and pumpable for extrusion. It needs to have a certain workability and flowability, meaning that it needs to pass through the nozzle without being interrupted. And then the buildability. We need to be able to put layers on top of each other without having the structure to collapse. That will also require a certain open time. We have a certain time to be able to do all these things, and we know that the flowability is going to change with time. And then the cement ink needs to set rapidly and with a high resistance to adhesive failure. So all of this requires that the cement ink we have a greater control of the hydration kinetics, of the rheology, and the structuration rate to ensure buildability, shape, stability of the printed layer. All right, so that's common for that we print large scale or on a small scale. But when considering small filament extrusion, small diameter extrusion, then there is additional consideration looking at the filament formation. And what we observed is that, well, the admixture and the type of inclusion, in fact, affect that formation, the formation of that extruded filament. For example, we saw with the addition of carbon nanofibers, we're having under extrusion. So there is the cement ink undergoes under a dynamic evolution as we print. And this is important when we are looking at very small diameter filament, because that's going to impact the formation of that filament, and that's going to impact also the property of that filament. So the extrusion pressure results in liquid phase filtration and in water segregation. So what we had is that we had a dynamic evolution of the water to cement ratio, of the local water to cement ratio as we print. Okay? So how can nanoparticles, what are the benefits of nanoparticles in 3D printing? And can nanoparticles help with the filament formation and also controlling the mechanical properties of this filament? So because of the large surface area, we know that nanoparticles, and we have heard that, can improve, benefit concrete by improving the rheology, the sealing rate, reducing the porosity, which lead to microstructural densification. And this in turn results in improved mechanical performance and durability. However, the specific role and effectiveness of the nanoparticles in the context of 3D printing needs to further investigation and needs to be better understood. Okay? So what we did, we used for this particular research, we have done some research with carbon nanofibers and nanotubes and graphene, but for this particular research, we look at the use of Halloysite Nanoclay. That is a naturally occurring mineral that is characterized by a two-layer tube structure. So in fact, it's a nanotube. It has an outer silica layer and an inner alumina layer. And the goal that we have here was to investigate the impact of Halloysite Nanoclay on the property of the hardened filament and on the printed structure. So for the interest of time, I'm going to present here results on the effect of Halloysite Nanoclay on the hardened filament. So we use type 1-2 Portland cement with and without, so we use a 5% cement replacement with Halloysite Nanoclay at a water to cement ratio of 0.3. The specimen that we print include rectilinear columns and concentric beams here. And we also had cast companion specimen that were made at a water to cement ratio of 0.3, but also at a water to cement ratio of 0.5, because we wanted to be able to compare this to that dynamic, because we had a dynamic evolution of the water to cement ratio in the filament, so we wanted to have something that we could compare. So let's talk about some of the results. So first, qualitative results. Okay? So what we saw is that the addition of this halloysite nanoclay significantly improved the extrudability. Keep in mind that we are working here with cement paste, and as Constantine mentioned, it's extremely difficult to, in fact, print with cement paste. It's much easier when you start adding aggregates. So that nanoclay improved the extrudability, and that by enhancing the extrusion consistency, and that led to much less discontinuity during the printing, and we didn't see that under extrusion that we were seeing without the halloysite nanoclay. So that led to a decrease in air void and the larger pore that we were seeing when we didn't have this halloysite nanoclay. So that the nanoclay enhanced the viscosity and minimized, which is what we were looking for, was to minimize that water segregation and that change in that water to cement ratio. So that was great. That did what we wanted to do. So that improved the buildability and decreased the deformation of the specimen as we were building the layer on top of each other. So then we wanted to look further and see, okay, what is the microstructure? Let's take a look at the filaments that we have. Let's take a look at the property of these filaments, because these properties, this is what's going to give us the macroscale property, that the overall property of the structure. So we wanted to have a better idea of what we were getting. The filaments were much better with the halloysite nanoclay, but we wanted to have a better understanding of that. So we look at microstructure, we look at different filaments, and then what we saw that we had clusters. We had clusters of, even though we took all the precaution to disperse them, we still had some clustering. But furthermore, by looking at different filaments, what we observed is that, well, we had, the clustering was, and the number of clusters that we had was different depending upon the filament. So that indicated that we had, during the extrusion, we had migration of the cluster and the nanoclay. And then, interestingly, is that for the cast specimen, well, the cluster that we had in the cast specimen were much larger than the one that we had in the printed filament. So 3D printing here helped breaking up this cluster. So we see that there is an effect already on the 3D printing, okay, in terms of the migration of the clusters and in terms of breaking up these clusters. So then what we wanted to do is, well, what are the mechanical properties of this filament? Can we understand the modulus of the filament, and can we see the effect, on that we see from that lack of dispersion? So we did nano indentation, and we did grid nano indentation on different filaments. And the grids where we went through over 1,000 indents to be able to have a good statistical analysis. And this is what we have. So that gives us the mechanically distinct phases, that give us a distribution of modulus. So what we have here, these are results for the cement ink that didn't contain the halloysite nanoclay. And what we can see is we have on the left-hand side, we have the 3D printed filament. On the right-hand side, we have the cast reference sample at 0.3 for the water-to-cement ratio and 0.5 for the water-to-cement ratio. And what we can see is first that we had the modulus distribution varies among the filaments. And what we were able to see is that we had two categories, in fact, of filaments. We had filaments that we categorized as high mechanical property filaments that had a high modulus value, and then so that we call HMP filament. And then we had filaments that had a low modulus value that we qualify as LMP filaments. And then if we look at the cast reference with the 0.3 water-to-cement ratio and the 0.5 water-to-cement ratio, basically what we see is that the higher water-to-cement ratio correlates with the lower modulus value. That makes sense. But then when we look at the 3D printing, that translates into that the modulus of the printed filament is, in fact, affected by that water-to-cement ratio change that we see during the extrusion. Okay? All right, so that's what we had when we didn't have the Halloysite Nanoclay. So now, what is the impact of Halloysite Nanoclay? Because the 3D printing obviously had an impact on our mechanical property of the filament itself. Okay? So then we did the same thing. We did nano indentation on filaments. We used grids of thousands of indents. And what we found is, well, we had, even though we saw a good, visually, there was the filament formation seems to be good. We didn't have any under extrusion. We had a better consistency in the filament. We still saw here that we had, again, different category of filaments. We had some that had high mechanical property filament and some that had low mechanical property filaments. But interestingly, we saw in the presence of the Halloysite Nanoclay, we saw a strengthening, at least for the high mechanical property filament. But we didn't see, if we look at the cast, we didn't see any real change on the median modulus of the cast specimen. So we can see that there is an effect, definitely, of the extrusion pressure and on the 3D printing on the property of the filament. So then we look at the two categories of filament, the high mechanical property filament and the low mechanical property filament, and we look at the distribution of modulus here. And what we can see, we know that the water segregation here was not the main factor. Okay? However, the migration of the nanoclay during the extrusion influenced that the stiffness, how the stiffness was distributed among the filament. So we had this the lower modulus that we see here for the LMP filament that correlates with a greater clustering of the nano halloysite. And if we look at the high mechanical property filament, this one here had a much higher modulus than the cast specimen. So again, we have an impact of the 3D printing on the mechanical property of this, on the modulus of the printed filament. So then, but this was giving us only the mechanically distinct phases. We didn't have the correlation with the chemistry. So what we wanted to do was to correlate chemistry and mechanics and the mechanical property. And we wanted to see what was the signature of these indents. So we look at the signature, the chemical signature of the indents. And we did SEM analysis coupled with EDS analysis. And by doing this here, we have on the left, we have the filament with the Halloysite Nanoclay. On the right, without the Halloysite Nanoclay. And what we can see is first that for both, we have a high proportion of indent that were associated with mixed phase. In fact, we indent on a lot of indents were on mixed CSH and CH phase. Okay? And then we can see here the indents that are associated with the clusters. And they have a very diverse composition that indicate the presence of hydration product within these clusters. Something that we also saw is that we had more IL-rich indents in the presence of the nanoclay, which indicate that we had, even though we had a cluster, we had dispersed fibers of nanoclay, and we also had formation of aluminate phase in the presence of this Halloysite Nanoclay. So then what we did is we look at this chemical signature for the high mechanical property filament and the low mechanical property filament, these two categories of filament. And this is what we look at the cast reference. And this is what we were able to see here, is that we found that we had a more AL-rich phase for the LMP filament, and we also had more CSH that were produced for this filament. So we had an increased pozzolanic activity for that filament. And this indicate that the concentration of dispersed Halloysite Nanoclay we had for this filament was much greater than for the high mechanical property filament. All right, so now we have the chemical signature, we have the mechanical property of this filament. So what we wanted to do, we wanted to couple the two and see what we had. Okay, so we put the two together, and this is what we found. So we have on the left here, we have the cement ink with the Halloysite Nanoclay. On the right, we have the cement ink without the Halloysite Nanoclay. So what we see here, let's say we take a given specimen. For a given specimen, we have the peak, the modulus, we have similar modulus peak across the different hydrates. Doesn't matter that we have CSH or we have a mixture of CSH and CH or we have CH. They have a similar modulus. And then if we look within each ink also, because by doing this comparison here, assemblage allowed us to have the proportion of hydrate that we have and in addition to their mechanical properties. So by doing this, we didn't see also, if we look at within the cement ink, we do not have a significant change in proportion within the same ink. So, but yet, we can see that we have, in terms of the modulus, we can see the shift in the peaks between the high mechanical property filament, the low mechanical property filament, or the cast references. So that indicates that the change, these differences were due to the microstructural arrangement rather than a change in their proportion. So basically, 3D printing affects the arrangement of the hydrates as we extrude. And again, it's because we have a small size diameter filament. But we wanted to try to use that to our advantage to try to control the microstructure. So there is, even though yet we cannot do that, but we know that it affects the microstructure and the arrangement of our phases, hydrates. So we wanted to go further. If that has an effect on the arrangement of the hydrates, well, does it change our CSH? Do we have an effect of the 3D printing on the CSH, high density, low density CSH? And do we have also an effect of the Halloysite Nanoclay, the Halloysite Nanoclay? So what we did, we look at the indents that were only pure CSH phases, and we look at their mechanical at the modulus, and we organize them in terms of low mechanical, low density CSH, high density CSH, and ultra high density CSH. So we have at the bottom, this is the results for the cement ink without the nanoclay. At the top, this is the cement ink with the nanoclay. And so what we see is that, well, the small diameter extrusion definitely impact the CSH packing density. Okay, so and we can see this from without the Halloysite Nanoclay, and then when we add the nanoclay, then the CSH phase is definitely affected by the nanoclay concentration and that clustering dynamic that we saw within the printed filament. So the concentration of nanocyte and the dispersion affect that packing density. If we look at the high mechanical, the one that had the high mechanical property filament, we had a lower concentration of nanoclay and lower concentration of cluster there, and that form high density and ultra high density CSH, versus when we look at the low mechanical property filament, here we see that the high concentration of Halloysite Nanoclay and the cluster completely interrupt the hydration matrix, and now we had a much lower modulus for the lower CSH density here. So there is definitely an effect of 3D printing on the CSH and the type of CSH that is being produced, and also an effect of the Halloysite Nanoclay. So in conclusion, okay, again, our goal here is we are trying to develop new materials. So we wanted to understand the formation of the filaments. We wanted to understand the mechanical property at the filament level, and can we control the microstructure? Can we control the mechanical property? Can we align, the hydrates inside of the filament? And so what we saw here, so it's still ongoing research, we saw that we have this for small filament extrusion that impact definitely the mesoscale assemblage of the hydrates. Without the addition of Halloysite Nanoclay, we had a dynamic change in the local water to cement ratio. When we add the Halloysite Nanoclay, we had now a dynamic evolution of the halloysite concentration within the filament and the clustering. The Halloysite Nanoclay definitely improved the printability and limited the extrusion-driven water-to-cement ratio change within the printed filament. And then that concentration of halloysite in cluster and in dispersed state affect the micromechanical properties and the packing density of the CSH. So with this, I'm going to acknowledge the funding here, and I will be happy to take any questions.
We still have a couple of minutes. If you have any questions, please use one.
Thank you very much. Very interesting. My question is about the effect on the properties due to the thin nozzle. I can see, but I'm not sure, how that the aspect ratio between the nozzle length and the nozzle diameter is very high. So we probably are producing a clear tribology. Do you think that this is the reason? Because it's a small nozzle, you have a good percentage of a bulk flow versus a lubrication layer, and when it's a bigger nozzle, this effect reduces?
Yeah, I know, absolutely. I think you have, that's a very good question and very good comment. That's definitely related. That's why I was very careful when I start introducing this, is that the mechanism that we are seeing are because we are printing with a small diameter, that if you start, and we are doing some where we are enlarging this, I don't know up to what size the diameter we need to go. Again, I wanted to try to control also the property. So I'm interested, in fact, in having this mechanism here.
Absolutely.
Okay, but yes, if we start going to larger scale, some of these mechanisms may not be seen. But my purpose, or what we are doing, is trying to, can we design new material with new property that we can control? And again, the application will be bricks or blocks, so we can, upscale a little bit. But I don't think that will be applicable when you start upscale.
I think you have shown that with the additives that you put, that might significantly change the tribology itself and result in, and that might be the reason why you have a smaller effect when you add those additives.
Yes, that's yeah, but that's exactly, yeah.
Very
yeah.
interesting. Thank you very much.
Thank you. Any other questions?
So you have the high and the low mechanical properties. Were you seeing a correlation between time, so basically when that bead was printed, or was it dispersed throughout the entire print process?
That's an excellent question, because when we first started, when my student came to me and told me that, well, he was seeing these two things, I say, oh, all right, it has to be, at the bottom versus the top, and I'm like, okay, you need to tell me which one it is, and then we did more, and then he's like, no, it has no correlation. So it didn't have any correlation.
Okay.
We were not, at least at this point, with what we did, we were not able to find any correlation, which I was surprised.
Okay, one more question.
Just follow up on this distribution of the elastic modulus. So you had a high modulus, I think, peak for some composition. Maybe you can explain a little bit more about this high modulus effect. So what do you think is causing this?
Oh, the distribution, these are different phases. So basically what you're capturing, it's it's called the mechanical, phases, okay? So they are not related yet to, in fact, they are related to hydrates, to unhydrate particles, so the one that are higher modulus, they will be the unhydrate particles. The main peak that you saw, and that's the one that I've been focusing on, are all the hydrates. And then we did further the convolution because, there's a lot of, statistical analysis.
But I
and
realize you have like high peak
Yeah,
there, and those who I think, and maybe it's like interesting to target, but maybe.
Yes, because what we saw also is that we had the extrusion pressure also induce dissolution of some of the unhydrated particles. So we were able to see that. We had that in one of our papers actually.
Okay, last question.
Earlier you mentioned that because of the fiber shape of clay, it could be reinforcing. So did you measure any fracture or mechanical properties?
We do have some mechanical property. I didn't want to show that, okay? We saw some improvement in some flexural, yes. What we saw also is that when we do the testing, we have much more repeatability than when we don't have the nanoclay, okay, because of the consistency, yes, yeah.
I'm just curious, how did you had a plot of calcium to silica ratio and how did you measure that? How with ESEM?
The
Calcium to silica ratio.
Yes, we did mapping of this of all the indents. So we had 1,000 indents. We did mapping on and we collect
with SEM.
We have EDS. Yes.
And how do you remember? What was the spatial accuracy?
Of the indents? I think we have the indents are separated by 10 micron. I mean, whatever it's used so that we don't have interference and yes.
So this is the one of two sessions. Right after this at 11 o'clock, we have the second part of it. We hope you can still join us. So with that, let's give another applause to all the speakers.